All right, we are jumping straight into conditional memory via Scalable Lookup, a new axis of sparsity for large language models. This one comes from Xin Cheng and the teams at Peking University and DeepSeek AI.
And this paper is, it's a huge rethink of the architecture, especially as we're all pushing deeper into sparse models.
Absolutely. Okay, so for everyone who wants the 60-second version, here's the rundown. The core idea is a new module they call Engram. Think of it as a complementary sidekick to the mixture of experts, or MOE approach we're all familiar with.
Right, but it provides a totally different kind of sparsity. Engram uses a souped-up Engram structure to do constant-time knowledge lookup. We're talking O1 retrieval. It's fundamentally different from compute.
And the big discovery, the thing that really validates this, is a clear U-shaped scaling law they found. This is basically the first hard proof that splitting your sparse capacity between MOE and Engram is strictly better than going pure MOE.
Yeah, that sweet spot seems to be around 75 to 80% for the MOE side. But what really sells it for me is just how broad the performance gains are.
That's the crazy part. The Engram 27B model didn't just get better at knowledge tasks, which you'd expect. MLU was up over 3 points. But general reasoning BBH jumped by a massive 5 points. ARC challenge up by 3.7. The gains were just everywhere.
Mechanistically, it's because Engram is like adding functional depth to the network. It handles the boring job of reconstructing static facts, which frees up the early layers to do actual, complex reasoning.
And the final killer feature is system efficiency. Because Engram's lookups are deterministic, they can stick absolutely gigantic memory tables. We're talking 100 billion parameters on slow host memory, like your system DRAM.
And the inference hit is tiny, less than 3%. So you can basically bypass the GPU's high bandwidth memory bottleneck. It's a really clean hack.
That ability to just scale up the knowledge without scaling the active compute budget. That's the real breakthrough.
It really is.
Okay, so let's unpack all of that. Before we even get to the Engram module itself, we need to talk about why it even needs to exist. It all boils down to this dual nature of what a language model is doing.
Precisely.
Yeah.
Anytime an LLM sees a piece of text, it's doing two very different jobs at once. First, there's compositional reasoning. This is the hard stuff, dynamic logic, solving a math problem, getting a subtle joke. That requires deep computation.
And the second job is just simple knowledge retrieval. This is all the static local stuff. Knowing the Pacific Ocean is a place, or that E equals MC squared, or just recognizing a common phrase like Diana, Princess of Wales.
And the fundamental problem with a standard transformer is that it uses the same tools for both jobs. It doesn't have a dedicated lookup table, so it has to simulate retrieval using its most expensive machinery, the attention and feed-forward layers.
Yeah, it's like having to rederive 2 + 2 = 4 every single time instead of just knowing it. When the model sees Diana, Princess of Wales, a whole bunch of early layers are just burning cycles to piece that static concept together.
It's just depth wasted on reconstruction. Think about it. Those first few layers could be figuring out the high-level structure of a really complex argument, but nope. They're stuck recognizing a named entity.
And that's where Engram comes in, to handle that static part efficiently.
Exactly. We already know MOE is for conditional computation routing to the right specialist for the logic. Engram is for conditional lookup grabbing the right fact for memory. It takes the classic Engram idea and makes it a real part of the architecture.
So let's get into that architecture. This isn't just something slapped on the front end, right? It's woven into the transformer backbone and works in two main phases.
Right. Sparse retrieval, and then context-aware fusion.
Okay, phase 1, sparse retrieval. First thing you have to deal with is just the insane number of possible engrams. How do you even begin to map that?
They start with a really clever trick called tokenizer compression. So standard tokenizers can be super inconsistent. The token for Apple with a capital A might be totally different from Apple with a lowercase a and a space before it.
Right, and for just knowing a fact, that distinction is totally irrelevant.
Exactly. So they pre-process the vocabulary. They run a function that standardizes all the raw token IDs using things like Unicode normalization and lowercasing so that words that mean the same thing actually map to the same ID.
And what kind of impact did that have? Just that one cleanup step?
It was huge. For their 128K tokenizer, it cut the effective vocabulary size by 23%. So you're massively increasing the semantic density of your knowledge base before you even build it.
That's brilliant. Just clean the data first.
Yeah.
But even then, the space of possible engrams is astronomical. How do they map those into a memory table that can actually fit somewhere?
That's where hashing comes in. They call it multi-head hashing. You can't possibly store an embedding for every single sequence, so instead they use a deterministic hash function to map any given engram to an index in their big embedding table.
Hang on, but if you're using hashing, don't you run into collision problems? Where two totally different phrases accidentally map to the same memory slot and corrupt the knowledge?
That's the classic problem, yeah. And they get around it by using multiple hash heads. So for each engram, they actually compute, say, k different hashes using k slightly different hash functions.
Ah, so it maps to k different spots in memory.
Right. It provides this built-in resilience. And critically, the whole retrieval process, the hashing, the lookup, is constant time. It's O1.
One is the magic phrase there. It doesn't matter if your memory table has 1 billion or 100 billion entries, the lookup time is always the same. That's what makes this so scalable.
Which brings us to phase 2, context-aware gating. Because like you said, a static lookup vector for, say, the word bank doesn't know if you're talking about a river bank or a financial bank.
It has no context, so you need a way to filter it. How does the model do that?
It uses the current hidden state, which has already processed the sentence context through attention as a sort of dynamic query. It takes that retrieved static embedding, et, and projects it into a key and a value.
So it's basically asking the hidden state, hey, does this fact I just looked up actually make sense with what we're talking about right now?
Exactly that. It computes a little scalar gate, alpha, based on how well the hidden state aligns with the retrieved key. If the context is about finance and the memory is for bank, that gate opens wide.
But if the context is about geography, the gate for the financial bank slams shut, filtering out the noise.
Yeah, they have a great visualization in the paper showing this. The gate fires up for real named entities like the Milky Way, but stays quiet for common words. They also add one little refinement, a quick, depth-wise causal convolution.
Just to sort of smooth things out and add a bit of nonlinearity before it gets added back into the main path.
Yep, exactly. It just makes the fused vector a little more expressive.
Okay, one last detail on the architecture. They built this for a multi-branch model, right? The MHC one.
Right, which has 4 parallel branches.
How do you handle that without just quadrupling your parameters?
Clever parameter sharing. The giant embedding table and the value projection matrix are shared across all 4 branches, but, and this is the key, each of the 4 branches gets its own unique key projection matrix.
I see. So all 4 branches are looking at the same big book of facts, but each one has its own special lens for deciding if a fact is relevant to its own little computation.
Yeah, we got it. It's that blend of structural efficiency and functional specificity.
Okay, so that's the how. Now for the really big question this paper answers. How should we spend our sparsity budget? This gets us to the sparsity allocation problem.
Right. You've got a fixed number of inactive parameters you can afford. How do you split them between MOE experts, which is for compute, and Engram, which is for memory?
And before this paper, I think the default assumption was just more MOE is always better, right? Go 100% on the experts.
And this paper just completely demolishes that assumption with that U-shaped scaling law. Pure MO is not optimal.
So tell me about that U-shape. How big of an improvement are we talking about at the bottom of that curve?
In their 10 billion parameter models, moving from a pure MOE setup down to that sweet spot of about 80% MOE, the validation loss dropped from 1.7248 to 1.7109.
That might not sound like a huge number, but for LLM training, a drop like that is a really big deal.
It's massive, and it proves this complementarity idea. Too much MOE and you're wasting compute on retrieval, too much Enneagram, and you lose your dynamic reasoning power. You need both.
And because the lookup is O1, they could just go crazy with the memory scaling, right? This infinite memory scaling idea.
Totally. They tested adding up to 13 billion extra parameters just to the memory table.
What happened? Did it plateau?
Not at all. It just kept getting better following a really clean power law. The log linear trend was perfect. It really validates that conditional memory is its own separate scalable axis you can push on.
You can just keep feeding it more knowledge without bloating your inference costs.
That's
incredible. Okay, let's look at the large-scale results. They trained these models on 262 billion tokens. What was the head-to-head comparison?
It was a super clean experiment. They took a strong MOE 27B model with 72 experts and pitted it against their Enneagram 27D model. For that one, they cut the experts down to 55 and poured the saved 5.7 billion parameters into the Enneagram memory.
And critically, both models had the exact same number of active parameters and the same FLOPs per token. It was a pure test of where you should put your budget.
And the results for Engram were just better everywhere. That was the most surprising thing. You'd expect it to win on knowledge tasks, but it won on reasoning too, big time.
Let's run through the numbers. Knowledge, MMLU up by 3.0, CMMLU up by 4.0. But the reasoning tasks, the complex stuff. BBH jumped by 5.0 points, ARC challenge up 3.7, code, math, everything got better.
It just shows that when you free the main computational engine from the boring task of fact lookup, it gets dramatically better at its real job at problem solving. It's a massive efficiency gain.
And they even showed that this trend continues. They built an Engram 40B model with an even bigger 18.5 billion parameter memory table, and the training loss just kept on dropping.
The model is still hungry for more facts. It hasn't saturated.
So this leads to the next question.
Yeah.
How? How is this actually working? They had a hypothesis that it's basically making the model deeper for free.
Yeah, functionally deeper. To test it, they used a couple of cool analysis tools. First was Logit Lens, which kind of measures how close a given layer is to making the final prediction.
And what did that show?
It showed the Engram models have a consistently lower KL divergence in the early layers. Basically, the model gets confident about its prediction much, much faster. It's accelerating how quickly it can compose the features it needs.
But the really convincing proof came from centered kernel alignment, CKA. That's the one that compares the representations between layers in two different models.
And CKA gave them this beautiful, clear result. The similarity diagonal shifted way up. To put it simply, the stuff being computed at layer 5 in the Engram model looked almost identical to the stuff being computed at layer 12 of the pure MOE model.
Whoa. So you're getting the reasoning power of a 12-layer model for the price of a 5-layer model, at least in those early stages.
That's a great way to put it. It's a huge shortcut.
And that shortcut has big implications for where you should even put the Engram module.
For sure. If you put it too late, the model's already wasted compute trying to reconstruct things. Put it too early, and the hidden state doesn't have enough context for the gating to work well.
So what was the sweet spot?
They found that a single module at layer 2 worked best. Just one round of attention seems to be enough to get a good context signal.
But the best overall was a layered design.
Yeah, a smaller module at layer 2 to do the early offloading, and then another one at layer 6 to leverage a richer context for more nuanced gating.
And their ablations also confirmed that all those little architectural details we talked about, like the context-aware gating, were super important, right?
Absolutely. Ripping out the context-aware gating was one of the worst things they could do to the performance. Static lookups by themselves are just not enough. You need that dynamic filter.
Okay, and the final nail in the coffin was the functional analysis, where they just turned Enneagram off during inference.
Right. And when they did that, anything that required factual knowledge just collapsed. Trivia QA performance dropped to just 29% of its original score. It proves Enneagram is where the facts live.
But, and this is the key tasks that depend on the input context, like reading comprehension, were mostly fine. They kept over 80% of their performance.
Because those tasks rely on the attention mechanism in the backbone. It's this perfect division of labor. MOE handles the dynamic context, Ennegram handles the static facts.
And freeing up that attention mechanism also gives it a massive boost for long context tasks.
A huge boost. They did this great ISO loss comparison. They took the Ennegram model from an earlier training step and compared it to the MOE model from a later step, so both had the exact same training loss.
A truly fair fight.
And in that fight, Ennegram was way better on long context retrieval. Multi-query NIH accuracy jumped from 84.2 to 97.0. The ability to keep track of details over a long window is just way better.
All right, finally, we have to talk about the infrastructure efficiency because this is maybe the most practical killer feature of the whole thing.
It's a huge deal. With MOE, the routing is dynamic, so you never know which expert you'll need next, which makes memory access tricky. But Engram is totally deterministic. The lookups only depend on the input tokens.
That predictability is the key, isn't it? It's what lets them do this prefetch and overlap strategy.
Exactly. You can take that gigantic 100 billion parameter memory table and stick the whole thing on cheap, slow system DRAM instead of precious GPU HBM.
So as the GPU is churning through, say, Transformer Block 5, the system is already looking ahead, knows which embeddings it'll need for Block 6, and starts pulling them from DRAM over the PCI bus.
Right. You're overlapping the slow data transfer with the fast computation. That way, the data arrives just in time, and the GPU never has to wait. You've effectively hidden the latency.
I love that, and the numbers back it up. Offloading a 100 billion parameter table to host memory only added a 2.8% throughput penalty.
It's basically free. It proves you can have a model with a truly gargantuan knowledge base, trillions of parameters of facts, without grinding your inference to a halt.
So to wrap this all up, the main takeaway seems to be that conditional memory, this Engram idea, isn't just a nice-to-have. It's a fundamental architectural piece we've been missing.
For sure. It fixes this core inefficiency of making our compute layers do a memory layer's job. The result is just better performance and way better system efficiency for the same budget.
And the really fascinating part from the CKA analysis is that doing this doesn't just make the model a better fact checker. It actually frees it up to become a better reasoner.
Which leaves us with a final thought for you, the listener, to chew on. For years, we've thought of LLMs as these uniform computational graphs. This paper reframes them as information dispatchers, routing tasks to either a reasoning engine or a knowledge base. If we accept that, the next big challenge isn't just about making models bigger, it's about designing better reasoning engines now that we've solved the knowledge problem. So what comes after MOE and Engram? What's the new module that's purely designed for that higher level compositional thought?